Well, hello everybody. If you can sit down and get ready. We are here with Nicolas Venegas. He works for the Bitbucket team, and today he will show us how to build healthy web apps. Thank you, Nicolas.
Thank you. Thank you for that warm welcome. It was great to see a lot of people today wearing the Bitbucket shirt. That's very humbling, especially on a day like this when it's really hot outside and you're wearing a black shirt, so good on you. Thanks for that. So today I'll be talking about some performance problems that Bitbucket has had and how we've kind of delivered some tools to help overcome them and kind of continuously inspect our environment as it's going. So first of all, before we get into everything, I'd like to introduce some of the cast of characters that will take us through this journey. Of course, we have Bitbucket. So if you're not familiar, Bitbucket is a code hosting website that provides free private code hosting. It's definitely one of the most popular code hosting websites on the internet. Now, I couldn't say it's the most popular code hosting website on the net, but it's certainly a popular code hosting site. And a bit of background, it was developed, initially founded by Jesper Noah in Copenhagen, Denmark, and then acquired by Atlassian in Australia a couple of years ago. And that's where I come into the picture and have been a Bitbucket developer for about a year and a half now. It's great for me today because I can kind of showcase some of the great work that the other members in our Bitbucket team have developed. So first of all, Erik van Zeist, a lot of props must go to him. He developed a couple of the libraries that I'll talk about today. And he also originally wrote and gave this talk. So a lot of credit to him for giving me the opportunity to give it to you and tell you that story. Brodie Rao is also another developer in the team, and he wrote one of the other libraries that I'll be mentioning. And finally, I'm just here, kind of the lucky one that can show off all this work, just narrate that to you and take you through that journey. So I'll give you a bit of a rundown of what we'll be talking about today. So like I mentioned, I'll be talking about performance. Now, performance in itself is kind of straightforward. I think it really only starts to become interesting when you have performance problems, and a lot of us do. Or maybe I should say, actually, speaking from personal experience, I've definitely had some performance problems in the past. So what I would like to do is focus on the kinds of things that you may not be aware of, the kind of things that happen in a development environment that you just may not see. Things that happen in your production environment that you may not see or may not be aware of. So these things don't exactly happen in your development environment simply because they're not slow there, but rather they're triggered by a whole slew of runtime factors that eventually do happen on your production environment and end up hurting real users. After that, I'll kind of recap some of what I think are the main causes of slowness in web applications and see some of their consequences. And finally, I'll delve into a few of the libraries that have been developed during the time in Bitbucket that have tried to address some of these things. I think the other really cool thing is I really love the naming that we have for some of our libraries, so you may get some insight into why they're named that way. So before I dive into the meat of everything and the technical details, I'd like to illustrate the problem I'll be talking about in this talk with a recent story from the Bitbucket team. So now, like I mentioned, Bitbucket is a popular code hosting website, and it's so popular in fact that we quite often have to buy new hardware to continue scaling up. So you can imagine that we'd have a very keen eye on the load of our servers. Yet for some reason, for the past couple of years, we've been running with a very serious performance problem that we saw almost every day. It literally stared us in the face whenever we ran the top command on our servers. It's ranked there number 1. But it was only a couple of months ago that we finally connected all the dots and realized that we were wasting a bunch of CPU cycles in an area of our infrastructure that really shouldn't have been using any CPU at all. So that area that we were wasting all that CPU cycles on is one particular program, a Python script called conc, which is part of our SSH infrastructure. Now, when you use SSH to communicate with a repository on Bitbucket, for example, when you use SSH to clone a repository, pull from it, or push to it, your SSH connection comes into our SSH daemon. Now, that's just a regular, standard SSH daemon. But once you're authenticated there, instead of giving you a regular Unix shell, what we do is we spawn this custom script, conc. Now, the job of conc is to locate your repository in the database. Once it's found it, we can know the path of your repository on our disks. And from there, we can hand over control to Git or Mercurial to do the actual work of fulfilling your operation, be it a clone, a push, or a pull. Now, that last step is quite expensive, but it's fine for Git and Mercurial to sit there with that open connection and just have its CPU ramp up to like 100%, start ballooning in memory, because it's actually fulfilling your operation. But it's not cool if conch does that. Really, conch is just our shell. So the only thing it should actually be doing is spawning off a Git or Mercurial process. But it turns out that conch was using a whole lot of CPU. And it only recently dawned on us that conch was importing a lot of Django code. In fact, it was using the Django ORM to look up your repository in the database. Now, Bitbucket is a fairly standard Django web application. So at the time, it made a lot of sense, and it was quite easy for us to just take that same code that went through the ORM and reuse that in conch directly. But that meant importing a lot of Django code and also some Bitbucket modules. And those Bitbucket modules, in turn, imported even more Django code. So this is all quite expensive, really expensive. I don't think anyone on the team really gave it a lot of thought as to how expensive that was. Turns out it was so expensive that it took 1.4 seconds to start this script. Now, if you then take the fact that we're spawning this script for every single incoming SSH connection, and that we have 50 such connections per second continuously, it doesn't take a lot of math to realize that that was wasting a whole lot of CPU. And once you realize this, that this script in starting up was wasting all that CPU, the solution is actually quite simple. Stepping back, conch, all it really needed to do was find your repository in our database. So it didn't really need to import all these things to start up. So what we did was simply remove those import dependencies for Django and Bitbucket code, and instead we just did raw SQL queries directly. Now, we deployed this fix, and you can imagine that the result was quite dramatic. So here is an actual load graph from one of our front-end machines. So we have a whole stack of these machines. They're pretty much identical. They all run the same stack, they all have Django, and they all accept incoming SSH connections. Now, we deployed this fix in May, and I think you'll notice halfway through the graph on May 15 was the day that we actually let it loose. And it was a pretty immediate result. Load went down by 60%, and I'm talking about all of our front-end servers. They all instantly went down in the same way. So in that one moment, it rendered more than half of our front-end machines completely redundant. So for a couple of years now, we had been spending money scaling up when really that was totally unnecessary. And it was great that a couple of guys in our team were able to identify and fix this problem, but in the end, still quite sad that all this money went to waste when the fix was so trivial. So it goes to show that even if you are reasonably conscious about performance and scalability, and I'd like to think that we are, given the number of users that we have, things like this can still slip through the cracks. And more to the point, I think it illustrates what this talk is about. Like, you can have some serious performance issues that don't manifest themselves in your development environment, but in your production environment, they can cause real problems and cause harm to a lot of your users. Now, in this case, I guess in our development environment, you could argue we should have seen that 1.4 second startup and fix that there, but we kind of ignored it, and it was a shame in this case. So now going back to web, sorry, yes? So the question was, how did we actually figure out it was taking so slow to start up? So I think for a long time we kind of just never made the connection that conch itself only spawns a process and should only have a small footprint in top. And then after a while, someone in our team, Dylan, just started asking the question, like, why is it still there? Why is it at the top? And then we ran it locally and finally saw that it was taking all that time to start up, and that kind of just triggered everything. So it was fairly easy in the end. So coming back to Django land and web servers in general, speaking from experience, I think a lot of problems that tend to cause these slow web applications ultimately point to a few common scenarios and problems that then cause this slowness. So I'll try and enumerate some of the problems that I think cause these things. So first off, the most common problem that causes this unexpected slowness, in my opinion, is anything to do with the database. So this could be slow queries or large queries that contain many table joins. Perhaps you're not even writing the SQL queries yourself. Perhaps you're using an ORM, and that ORM is producing SQL that is just not efficient for what you need it for. Maybe you're missing an important table index, or maybe you're just performing way too many queries. Now, all of this kind of stuff is usually fine in your local development environment because you're not really running with a database that's the size of your production one. For example, on my local machine, I run with a very small database, and so even the heaviest of queries performs quite reasonably quickly, and things just pass by me and I won't notice. Now, as an example of running too many queries, so this is another story that kind of demonstrates the vulnerable side of Bitbucket. I know we're like one of the top code hosting sites, but still we're a bit of an underdog, and so I hope these stories can kind of give you an insight into what we're about and how we go about things. So this one is a story about performing way too many queries. So at one point we had an AJAX endpoint that a lot of people were complaining was just way too slow, and even for some people it wouldn't return at all, it would time out. Now, in our development environment, hitting that endpoint, of course, it was reasonably quick. Like, we couldn't see these problems. But sure enough, when we checked the logs, we could see that it was timing out for these particular users. Now, it was quite difficult for us to reproduce this problem locally. That is until we replicated enough of the production environment locally. So in this case, that meant taking a full copy of the production database, which is quite large, and restoring it on our local machines. And once we did that, we could log in as the affected users. And sure enough, as soon as we requested that same AJAX endpoint, the request would time out. So in further investigating this, we let the request continue without any timeouts imposed. And when it finally returned, it ended up executing about 100,000 SQL queries, which is pretty insane. So now, when we were developing this, this wasn't a problem in our development environment. And even with that production database, using our own personal accounts, we didn't see this problem either because it was quite context dependent on, say, the permissions you had set up in Bitbucket and the number of repositories you had access to. So this kind of shows that a lot of these performance problems tend to happen in these weird scenarios that are really context dependent. So that was pretty nasty. So the next common cause, I think, of slowness or unexpected slowness in web applications is anything to do with locking. So whenever you have concurrency in your web application, threads and processes, you will at some point need to use locks to prevent race conditions when concurrently modifying shared resources. So in using a lock, in acquiring it, you are deliberately reducing the concurrency of your application. But you're doing it quite consciously. But when you do so, you run the risk of really screwing it up. So I wouldn't be the first to admit that I've held onto a lock longer than I probably should have, causing the application to slow down or not do as much throughput as it could. So whenever you do that, your application runs the risk of slowing down. And in your production environment, that can be very evident when lots of people start going through this code and they have lock contention. Now again, in your local development environment, even if you acquire and hold a lock for the entire duration of a request, since you're typically only testing by yourself with that one request, you're not going to see this problem. But in your production environment, it's definitely going to be there. Now, another area where locks can be problematic is in the database. So there, some database manipulations may require, say, a row-level lock, or even worse, a table-level lock. Now, if these queries that require these locks take a long time to execute, for example, they take a long time to either commit or roll back, then any other queries during this time window that want to access those same tables may be blocked. Now, speaking from personal experience, some of the scariest moments I've had as a developer have been when I've rolled out a really innocent-looking migration to our production databases and just adding a column and a table that I was sure was very small, but it ended up locking the entire database and taking the site down for like a couple of minutes, and I just wanted to run away at that point. It was pretty scary. So another common cause of unexpected slowness in web apps can be excessive I/O, or really anything excessive. So here we have another fine example from Bitbucket. So in Bitbucket, we use Memcache, and Memcache is really awesome at making your application a lot faster if you use it wisely. In our case, for this particular story, we did not use it wisely. So what happened was we had a page that requested a certain value from memcache, given it the key, and memcache would respond via the network with the value for that key. Now, a little bit later on, it made an equivalent call using the exactly same key, passing that to memcache, and memcache very happily gave us the same value back across the network. So the problem in the code here was that it wasn't smart enough to retain that initial value that it already had. So it got worse from here. For one particular user, under a certain circumstance and configuration scenario, we ended up making this request to memcache over 5,000 times in a single loop. Now, even if that call to memcache is really quick, even if it's like 1 millisecond, at that rate you're still wasting about 5 seconds of time. So that's not good at all. Now, another common cause of unexpected slowness in web applications, although perhaps a bit less common than the others, are regular expressions. So now, the gotcha with regular expressions is that they can be very quick when passed one body of text, and then past a different body of text of, say, the same size, they can be excruciatingly slow. So, for example, this is a pretty extreme regular expression. We like to term it the evil regular expression in Bitbucket, and I'll go into the story about that a little bit later on. But basically, if you pass this, a document full of the letter A, it will certainly not finish before the day is out. So that goes to show that the performance of regular expressions can be very dynamic and can cause unexpected slowness. So at the end of the day, these common causes of unexpected slowness, again, are things that don't necessarily show up in your development environment, but in your production environment, they can really bite you because of their context-sensitive performance. However, once that does happen on your production environment, you tend to have very real consequences. So just going back to that example of Conch as part of our SSH infrastructure, like we wasted a lot of money buying machines when really that wasn't necessary. So some of those, so again, the slowness here is due to the context-sensitive nature of their performance. So now moving back onto web servers, let's start enumerating some of the actual real concrete consequences of this unexpected performance slowdowns. So one, if you have a request that is slow to complete, and you request that endpoint multiple times concurrently, and this might just be a user who's pressing refresh in their browser because they're not sure whether their request made it through the first time, this might constitute a denial of service. Another thing that can be that denial of service will happen because you're filling up resources, and in this case, that's your web server worker threads. So another thing that can be problematic is if you use a web server that has an automatic kill switch for long-running requests. For example, Gunicorn, which is what Bitbucket uses. So in Gunicorn, if a request runs longer than 30 seconds, which is its default timeout, Gunicorn will come in and kill that request. Now, these requests are separate processes, so effectively Gunicorn will kill that process. And the way it kills it is that it sends a sig kill to that process, to the kernel, which is a kill-9. Now, that is the most extreme form of killing a process because that process will be immediately taken out of the kernel scheduler. Now, this is pretty harsh because that means that the request that is about to be killed has no knowledge that it's about to be killed. Now, if it has no knowledge that it's about to be killed, then it has no chance to do any graceful cleanup or release any resources that it had. And for Bitbucket, this is a real problem because we do use log files in the file system to help us manage the Git and Mercurial repositories that live on our disks. So for example, if a request acquires a lock file on a repository and ends up taking a long time to process that request, it might be cloning or something like that, if Gunicorn stepped in and killed that process, that lock would still remain on the file system. Now, when the next request comes in for that same repository, it will sit there waiting for a lock that will never be released. So you can imagine what happens. 30 seconds later, Gunicorn comes in, sees that that request is still active, and then kills it. So now the next request will repeat this whole same process, simply because that lock hasn't been cleaned up. And worst of all, you'd be none the wiser about this, because this may be happening on a particular repository that no one really accesses. Plus, since Gunicorn kills the request, it leaves no forensic evidence behind that that request got killed. So basically, there's no way for you to spot the fact that this happened, nor is there a way for you to identify what the problem was and how to fix it. And so unless the user reports that their repository is now not working, you really don't know that this happened. And even worse, if the user doesn't report that this happened to you, they might just become frustrated with your service and stop using it. So again, Gunnycorn not leaving behind forensic evidence is really a bad thing for us, especially on Bitbucket. So I want to introduce a tool that can help find these kinds of problems. It's called dogslow, and it was written by Eric Van Zeiss from the Bitbucket team. Now, dogslow is a standard Django middleware that you can install and run on every request. Now, what it does is, for every request that comes through, it starts a timer, it lets that request continue, and then on the way out, it stops that timer. So since all it does is start and stop a timer, there is actually no risk in running this in your production environment for every request, since it doesn't actually use any resources. In fact, on Bitbucket, we've been using dogslow on all of our requests for the better part of a year now. Now, when a request takes longer than the configured timeout of dogslow, dogslow will step in and simply observe that request thread. So it won't actually stop that request thread, it won't interfere with it, and it won't interrupt it at all. And the best part is that request thread doesn't even know that it's being observed. So what dogslow actually does is just make a copy of the stack of that request thread, so essentially a snapshot of the stack at that point in time, and emails that trace back to you. So this gives you two things. First of all, you're now automatically alerted as to when a request is taking too long. And second of all, but more importantly, you now have a traceback that you can use to help you identify what the problem was and how to go about fixing it. So this helps to overcome the problem of your web server leaving no forensic evidence behind. Now here's an example email that dogslow actually sent while recently monitoring requests on Bitbucket. So you see in the subject... Sorry about that.
Gray font on the black background. What were you thinking?
I wasn't thinking, and I apologize for that. So this email, in the subject, in the URL, in the subject of the email will include the URL of the request that was too slow. Further down, there are timestamps that show when the email was sent and also when dogslow came in and took its snapshot. So in this case, it is set to timeout 25 seconds into a request. And that's just before the 30-second timeout that Gunnycorn would have imposed to kill the request. Now, I've edited the traceback, and even though it's not readable here, you'll have to trust me. The code path that we're looking at is that for the repository overview page. So the repository overview page contains the README file of a project, nicely rendered, along with the 5 most recent commits for that repository, so that you can very quickly gauge the recent activity of that repository. Now, for us to get the list of the 5 most recent commits, we end up calling a method called walk. And what walk does, so actually walk is part of our DVCS library Orochi, and it acts on the history of the repository. So now, walk is a context manager that ends up calling into revlist. And what revlist is that for every Git repository, we maintain an index on that repository. So it's not an index of the contents of the files or the files themselves. It's actually just an index of the commits in the repository, specifically their hashes, ordered by the chronological and topological order. So this is effectively the DAG that you see when you look at a Git repository. So the reason we have to do this is that it's not so trivial to calculate this in Git, because Git doesn't store that information directly. So basically, we have to maintain this index so that we can keep this in a speedy fashion. Now, this indexing by revlist is pretty quick. Even for large repositories, it should only take like 100 milliseconds, or at worst, a few hundred milliseconds. And we do this indexing the very first time we encounter a Git repository. We write that index out to a file so that it's cached. And then any time the repository is modified, we regenerate this index of commits. So now in this particular case, so again, this is an email from dogslow, so this was a request that was taking way too long. In this case, it was taking longer than 25 seconds to generate this index when calling revlist, when really we expect it to take 0.1 seconds. So it turns out it was so slow because this particular repository was fragmented. So just to give you a bit of background on that, in Git, Git can store the contents of a repository in a packed fashion. So what that means is that it will store in something called pack objects the entire history of the repository as some compressed archives. Now these are very quick to access since they're indexed. There's usually only one or a handful of them, so Git will end up memory mapping them, and it's all very fast. Now, again, this request was slow because the repository was fragmented. That means that these pack objects were exploded into thousands of tiny little files in the file system called loose objects, and that live inside the Git repository. Now, even though this repository was fragmented, it's still a valid Git repository. You can still do all the normal commands that you would normally do. Except the only difference now is that for some operations it's going to be very slow, since now it has to traverse thousands of these tiny loose objects in the file system, opening and closing all these file handles. And that was the case here. For this particular repository, it had almost 7,000 loose objects, all these tiny files that lived in that repository. And the fix for this is actually quite trivial. Git comes with some low-level tools that allow you to repack a repository. In this case, the command gc. So just running that command brought the call to revlist, this indexing operation, down from 35 seconds to 0.1 seconds, which is what we expect. Now, thanks to dogslow, we were alerted about this problem before the user even received a 500 page for it. That's because dogslow came in and took that snapshot 25 seconds into the request prior to the timeout of 30 seconds when that user would have seen Gunicorn kill their request. Now fixing this, again, was only a matter of minutes once we had located the repository on disk and run git gc. And fixing this for real so that in the future it does not happen to other repositories is again also trivial. It's just a matter of making sure that we run this git gc command periodically on repositories to do housekeeping. So already we can start to see how important this automatic alerting that dogslow gives us is. Because the user may not have reported that the repository was unresponsive. But instead, we were immediately alerted with a traceback that pinpointed the whole problem and allowed us to identify it and fix it almost on the spot. So given that dogslow gives you a snapshot of the traceback, you may examine one of the emails it sent you, and being familiar with the code and the method in question that was running when dogslow took a snapshot, you might infer that since you're familiar with that code, it is not a slow code path, and so it couldn't possibly be the cause of slowness in your application. So what must have happened was that while the request was happening, initially there was something that was slow, but then once that completed, the request continued with its normal work, and that's when dogslow stepped in and took that snapshot, effectively taking a snapshot of innocent code, or code that wasn't slow. So statistically speaking, this isn't that likely, but it can definitely happen. Or it could be that you have multiple hotspots in your code path, and dogslow was only able to take a snapshot of one of them. So in this case, you'd normally want to profile your application. So you'd hook up the profiler, rerun that same request, and then collect that profiling data so that you can analyze what happened to figure out the hotspot. But we've kind of already established that problems like these tend to not happen in your development environment, or they're difficult to reproduce in that development environment. So ideally, what you would like to do is profile the production environment. So that would mean hooking up a profiler and having it running for some period of time for all your requests, just so that you can profile a couple of slow requests. And by the very nature of profiling, it's going to slow down your application. It's going to make it very slow, perhaps by an order of magnitude. So hooking up the profiler to the production environment really isn't always a good option, or even a valid option. So for this, I'm going to introduce another tool that has been developed by Brodie Rao, another member of the Bitbucket team, called django-geordi. So Geordi allows you to profile individual requests in a Django web application and visualize the performance and call stack of that request. Now, given its powers of visualization, I think it's pretty cool that this library was named after Geordi LaForge from Star Trek: The Next Generation. So if you're not familiar, this is a character that was born blind, but thanks to the power of his visor, and in our case the visor middleware, he's able to see more than everyone else. So Geordi profiles individual requests, and it sits there in your production environment as a middleware, and normally it won't do anything. It will just sit there and pass requests through. So it's perfectly safe to run in your production environment. But as soon as you add the magic keyword to the URL, Geordi, it triggers Geordi for that particular request. So what will happen is that it will start the profiler, it will let that request run, although in a special way I'll elaborate on a little bit further on. And then once it's done, it will stop the profiler. So then it collects all that profiling information and presents that to you rather than the page that would have been rendered. And instead of providing just the raw profiling data, it actually generates a PDF of the call graph. So you're probably familiar with these. This is one of those huge call graphs that contains method invocations, color-coded by their cumulative execution time and the number of method calls. So they're absolutely great for finding hotspots in your program. So here's an example of the call graph that Geordi generated for a single request to the Explore page on Bitbucket, which is a page that lists repositories with recent activity. So you can see this screenshot just has like one portion of the call graph. It's much bigger than this. But you can zoom in, you can move around, you can save it, and hold on to that vital profiling information so you can go ahead and figure out what the problem is and fix it. Now, I did mention previously that profiling will make your application slower. So you may be wondering, like with a request that you already kind of identified as slow, if you now use the profiler for that particular request, are you running the risk of making Gunnycorn come in and kill that request? Or it could be the fact that you only want to profile things that are slow anyway, and maybe they're not making it past Gunnycorn's 30-second limit, or adding the profiler would probably make it more likely that it would get killed after 30 seconds. So to avoid that, Geordi has a really cool trick. What it does is that when it starts to profile a particular request, instead of running it through the web server, it will instead route that request through to a background task using Celery. So now the request can run without any timeouts and in complete isolation for as long as it needs to. So the page you're actually viewing when you add the Geordi keyword to the URL is simply an AJAX polling page that waits for that background task to complete. And that background task is your kind of original request that you're now profiling. And once it does complete, it renders the PDF in your browser like this. So at no time does Geordi put you at risk of causing any load problems or any denial of service problems on your server. Since even if you are doing multiple concurrent Geordi profiling requests at the same time, you're not actually using your web server's worker threads. You're actually just queuing up jobs in the background, and then they complete in their own time for as long as they need to. So this is a pretty unique way of profiling your production environment. Sorry, I have a question over there. Yeah, that's definitely true. So,
can you repeat the question?
Sorry, the question was, I think it's kind of along the lines of what I previously mentioned, where the request you're profiling without profiling itself is probably already slow, and then once you add the profiling, it's probably going to make it run a lot slower. So what we can overcome is the 30-second timeout that our web server would normally come in and kill that request. And the way we do that is we run that request in the background as a Celery task, and then it has as much time as it needs to. So like I mentioned, this provides a really unique way of profiling your requests in your production environment. It gives you all the power of profiling with a really low barrier to entry. Like you don't even need to, all you need to do is add that keyword to the URL, and you don't need to try to reproduce that production environment locally. Now both of these tools, dogslow and Geordi, are completely reactive in the sense that they will alert you when you have requests that run slow, and they will help you identify what the problem is, but they're not actually there to try to prevent the causes of slowness in the first place. Your users will still encounter slow requests, timeouts, and 500 pages. So in the spirit of being proactive about trying to prevent slowness in the first place, I'd like to introduce a third and final utility called interruptingcow. And I think this has probably my favorite name of a library ever. It was named after the favorite joke of the daughter of one of the Bitbucket team members. So interruptingcow was written by Eric Van Zeist, and what it does is it allows you to time box chunks of Python code. So I apologize for the quality of the text here for the code excerpt. But basically what it does is it provides a context manager where you can say, I want to run a piece of code with a certain timeout. So here we want to say that we want to run a regular expression, that evil one from before that will take forever, in a context manager that says, run this for a maximum of 20 seconds, and if it takes longer than that, please raise this exception. In this example, it's a runtime exception. Sorry, a runtime error. So now your code can simply time box that piece of code and then catch the exception that you specified if it does take too long. So here, this program will guarantee that trying to match this evil regular expression will only ever run for at most 20 seconds. So having this level of control in your web service is really useful. Like in Bitbucket, we use interruptingcow on every single request. Now what we do is we wrap every request in a timeout for just about as long as Gunicorn would come in and kill it, so around 30 seconds. And we don't even catch the exception that interruptingcow throws. Instead, we deliberately let that exception bubble to the top. So since it bubbles to the top and is uncaught, the page will fail in a similar way to Gunicorn having come in and killed that request. So to the user, the page fails in the same way. But to us, there's a crucial difference. By failing with an exception that is uncaught, we can allow that exception to bubble up the stack and trigger all our finally clauses, allowing us to clean up all the stuff that we may have been using. For example, the lock files that previously, if Gunicorn had come in, would have left on the file system. So even though we now fail in a controlled manner, and we avoid leaving this dirty state in the file system that would have previously survived the killed process had Gunicorn come in and killed it so viciously. So it's pretty simple, but extremely useful in this case for us. Now, there's more to interruptingcow, because it is also re-entrant, which means it supports nested timeouts. So basically, within a long timeout, for example, the one that we wrap each Bitbucket request in, we can have smaller timeouts that will time box other chunks of work. Now, this is really useful if you realize that some of the work that you do in fulfilling a request is kind of like an optional added-on bonus. Like, you can kind of live without it as long as that request finishes and it completes this entire task. But it could be that optional added bonus is maybe compute intensive and would make your entire request slow. So we can kind of now time box that thing that may be or may not be important and let the entire request only take a short time. So for example, in Bitbucket, we have a feature called linkers, which basically allow us to process user-provided strings. So for example, commit messages, comments, pull request descriptions. And what we can do is we can scan this user-provided text for things that look like chain set hashes, repository names, or usernames. And we can turn those pieces of text into hyperlinks. And the way we do that is by using a regular expression that we apply to the user-provided text. And as you're probably aware by now, regular expressions have very dynamic performance. And it can definitely cause unexpected slowness. So actually that regular expression I've been referring to as the evil one was actually the brainchild of one of the expert trolls in our team, Jesper, the founder of Bitbucket. We were about to release this linker feature, and like a light bulb went off in his head, and he kind of just hacked away and realized that if he entered a certain regex, it would just kill the machine. And so even though it delayed the release of that feature, it meant that we realized we had to implement nested timeouts inside interruptingcow. So in most cases, so what we do is when that piece of code that tries to hyperlink the user-provided text, we can now time box that in an interruptingcow timeout that is very small. And if that isn't enough time for the text to be hyperlinked, we can simply fall back to the raw user-provided text. So in this case, you wouldn't get that nice hyperlinked commit message, but in most cases, getting the commit message is the important thing, and having the hyperlinks are nice to have, but not having them is still, for us, a perfectly reasonable user experience. But to make that concrete, I have another code example, which may be a little bit hard to follow. We'll see. So we have an outer timeout that is a long one, here 20 seconds, that raises one kind of exception called outer exception. And then within that, we have a context manager that has a smaller timeout, this time of 1 second, and it raises a different kind of exception. So within that inner timeout, we can try an expensive operation that maybe we don't necessarily need. If it does take too long, we can just catch that inner exception and then do a cheaper alternative that maybe gives us 80% of what we expect the user experience to be. So this is nice. This is a nice tool when you want to provide like a nice feature or user experience that isn't entirely necessary for the request to complete, and rather the request completing itself in a timely manner is the more important thing here. So as Bitbucket has evolved, So as Bitbucket has evolved and grown, we've seen the need for some of these tools. So first of all, dogslow can help you find problems that you may not have previously been aware of, simply because these kind of things only happen in your production environment, and then, for example, Gunicorn would have killed a request and you would have been none the wiser. So dogslow is able to catch those, and it even emails you a nice traceback showing you the likely source of the problem so that you can identify and fix it. In cases where that still isn't enough information, you can use something like django-geordi to profile specific requests in your production environment and get a nice call graph of their runtime characteristics and their call graph. And that's without the risk of causing load or denial of service problems on your server by running these geordi requests, because they run as background tasks. So combining these two tools are pretty cool in identifying and helping you fix problems that you might have. And finally, if you want to be proactive about preventing slowness in your web apps, you can use something like interruptingcow to time box certain chunks of code whose performance might be dynamic because, say, for example, they rely on user-provided input. And it's great because you can try that expensive operation, and if it does take too long, you simply provide a cheaper alternative to use. And finally, in cases where that doesn't make sense to provide a cheaper alternative, or there is no cheaper alternative to provide, you can simply use interruptingcow as a way to fail gracefully to ensure that all your exception handlers the exception raised by interruptingcow bubbles up the stack and triggers all the finally clauses so that you can clean up all of the resources that you were using. Now, all of these three libraries are open source, and they are on the Bitbucket website, so I hope you will check them out. And if you haven't checked out Bitbucket in a while, I think you might be surprised by some of the features we've had. Again, it's free private repository code hosting. We have Git support, fully featured pull request, team support, and even some Jira integration. So once again, I'd like to thank you guys for coming to this talk. One final thing. Tonight at Dublin Pub here in Florence, we're having a drink up hosted by Bitbucket. So myself, Nicolas, and the product manager for Bitbucket, Justin, in the back, will be there, and that's running from 7 to 9 p.m. So it'd be great to see you guys there and have a chat. So thank you.
So, are there any questions?
If you fork a repository with an issue tracker and you commit then a fixed bug, then you sometimes fix bugs in a different repository of the fork. Is that solved now?
I'm not sure if that's resolved. I will admit that the issue tracker in Bitbucket hasn't been paid as much attention as some of the other stuff we've worked on, but I think sometimes our code may get confused that fixing a bug by saying in your commit message fixed number 1 might also be interpreted in the parent fork once those changes are pulled in as having closed that. So yeah, take
you
note.
can use a hash, for example, instead of just a number?
We'll I'll definitely try to investigate that and see how we can resolve that.
Okay.
Thanks.
Dogslow, is that a pure Django application, or can you apply it to other frameworks like SOAP or?
You know, at the moment, I think it is implemented as a Django middleware. Now, I'm not entirely familiar with the internals of how that is implemented, but some of the techniques it uses may be completely relevant to something like that. So I'd encourage you to maybe check out the dogslow public repository and see if that might be applicable to you.
Hi. It occurs to me that the interruptingcow thing almost seems quite high in the stack to do that stuff, because I mean, is it specific to Gunicorn that it will kill it in a nasty way? So if you were using a different WSGI container to handle it better and maybe log things and then fire things off from that, wouldn't you? I don't know. Just to me, it seems like you'd normally do it at that level rather than.
Yep.
In
Yeah.
the
So I only have experience with Gunicorn from our use in Bitbucket, and it is due to the fact that Gunicorn uses sig kill, which is that extreme form of killing that immediately kills that process. So we do have it as like a middleware, interrupting cow is a middleware that will trigger high in the stack just before that timeout is hit from Gunicorn. So yeah, I think it's perfectly true that other frameworks or other WSGI containers might handle things in a more graceful way that can kind of require you not to use interrupting cow for that specific purpose, but it still has value, like I mentioned, in time boxing, smaller bits of code that you can have for a very short time.
Okay, but it is specific to being running on Unicorn that you would use it. I suppose you could use it on anything.
You can use it on anything. It's just a standalone Python library. It's just that we use it inside a middleware in our application to have that effect.
Thanks.
Hi. You mentioned several problems with your database. Can you elaborate more on that and which database you use in the backend? And did you also explore possibility of using NoSQL solution?
Right. So I'm not entirely familiar with the database situation we have, but we do use Postgres SQL. I don't know if we explored a NoSQL solution. I think for our event system, we do use Redis to store that information. So in that sense, we use it there. But I think that question might be better served by someone else in my team. So if you want to find out more, I can certainly forward you their details.
I have a slightly unrelated question concerning Bitbucket in general, because I'm working with the PyPy team and I see the PyPy repository being cloned about 3 or 4 times a week, yep. But not on their local machine as I expected, but they clone it onto Bitbucket. Okay. Is that a problem, or do you have some copy and write mechanism?
I think Mercurial, so PyPy repository is Mercurial, and I think when we fork that, we do use hard links, so we will put it on a piece of our file system that will contain hard links when you fork at that point. So for us, it's not really a problem that users use fork in that manner.
So it's hard links. That means if one file is changed, then that file will become real. So if I want to be nasty, I need to change every single file, right?
That's certainly something you could try. Again, we have a sysadmin who deals with the storage and stuff, so that it might be one of his problems that I can kind of keep out of my mind. So we'll see.
Thank you.
So you mentioned that Geordi runs the tasks in a separate worker pool, and presumably they're going to take a while, like they could be talking 5 minutes. Right. But are they running on the same server as well, and could they still be soaking up CPU?
Well, it depends on where you have your celery jobs consumed. So you may have them on the same server, or you might have a different server dedicated to do that. So it simply queues up that job in some kind of queue, and then that job will be picked up somewhere else.
Just one other thing, if you are dealing with user-provided regular expressions, look at the ORI2 library, which doesn't have exponential performance.
Okay. Yeah, I think actually for what we wanted it, there were some operations that we wanted to provide with custom linking, where you could provide your own regular expression that I think at the time when we developed it, we didn't quite see how we could use that particular library, but I think it's worth revisiting. So thanks. This one?
So you have got 1 second to do expensive thing and 19 seconds to do cheap thing. Shouldn't it be reversed? I mean, 19 seconds to do expensive thing and 1 second to do cheap thing.
Right, yeah. So this is definitely a contrived example. I mean, you probably have something a bit more reasonable, but this just shows that we are using a smaller timeout within a larger timeout. Like in Bitbucket, we have that timeout for the entire request, which is almost 30 seconds, and then we do time box smaller bits of thing here, smaller chunks of code here and there.
The Python package index page for interruptingcow says that it uses signals and so is incompatible with threads. Do you have any ideas whether it's possible to remove this limitation?
So I'm not entirely familiar with the implementation of that. So again, Eric wrote this library, so my knowledge of like Unix level stuff is not that great. So unfortunately, I don't know. So I'll have to pass that question on to him to figure that out.
Any other question? No? Okay. Thank you, Nicolas. Thank you very much. Don't turn it off, please.